All right. So, water. Chapter 3. Water and the fitness of the environment. So, when scientists were trying to find proof of life on Mars, they were actually trying to find proof of evidence of water on Mars. Because without water, there really is no life. Now, what? How is that possible? Now, let's go back and look at, again, the 8 characteristics of living things. All right? All right, don't take my word for it. Let's see. So, remember, how many are there? 8. Put them in alphabetical order. That way it's easy to remember what they are. Hopefully you remember C, D, E, G. Yes, I know we skipped F. H, M, R, R. 1, 2, 3, 4, 5, 6, 7, 8. Cells, DNA, evolve, grow and develop, homeostasis, metabolism, reproduce, and respond to environment. Okay, so let's see how many of these involve water. Cells. The next couple of slides you're going to see, but hopefully you know on your own. If not, it's okay. Like we said, it's coming up in the next few slides. Is water found in cells? In actuality, it is. 90 to 95% of your cells are actually made of water. So, yeah, most definitely. Do you remember what kind of bonds hold the 2 halves of DNA together? There were those weak bonds, hydrogen bonds. And where do you think the hydrogen comes from? H2O, water. So, yep. Evolve. Where did life begin on Earth? Water. Evolved from water into land. So, water. Yep. Grow and develop. Well, depending on who you talk to, we can only last 3 to 7 days without water. So can we grow and develop without water? No. So, we need water. Homeostasis. Can we maintain a constant body temperature without water? No. Okay, real simple. You get sick, where they tell you, drink fluids. Overheat, they tell you, quickly keep your fluids up, or get them back up if they went down. Anything, you've got to have water in you in order to maintain homeostasis. You need water. Metabolism, real simple. Try to eat a bunch of goldfish without water. Very hard. Try to eat crackers with peanut butter without water. Very hard. Now, there's more metabolism than just eating, but just for kicks and giggles right now, we're going to keep it at that. So, we need water. Reproduce. We need water for reproduction, and we're going to leave it at that for now. Respond to the environment. When you're hot, what do? You sweat. What do you sweat? You sweat water. When you're cold and you start to shiver, okay? You're shivering because your muscles are contracting and causing your muscles, so that your muscles can go ahead and shiver so that you can try and provide enough heat to warm you up. How do you get that energy? In the form of ATP, thanks to cell respiration. And you need water for all that to occur. So, you better believe whether you're hot or cold, you need water. So in all 8 characteristics, water's involved. So, that's why it's chapter 3. Here we go. Only things I need you to worry about are yellow. I apologize, first few slides are white, and then some go into yellow. That's what I really want you to worry about. So terrestrial life today still requires water to survive. Humans can survive weeks without food, 1 week, like I said, 3 to 7 days, depending on who you talk to, without water. 2 hydrogen atoms are joined to the oxygen by covalent bonds. That's our Mickey Mouse face again. The ears are hydrogen. The face is oxygen. So covalent bonds are right here because we're sharing the electrons unevenly. So we have slightly negative down here. We have slightly positive up here. So that creates a polar covalent bond molecule. 2 water molecules come together via electric attraction. and are held together by hydrogen bonds. So we have a second water molecule is going to come together right here. What is going to bond this molecule to this water molecule to the next one? That's your hydrogen bond. Okay? Because it's a hydrogen bonding to electronegative element. Okay? We're good? There are 4 big properties of water I need you to know. Cohesion and adhesion. Let's start with those 2. Here's an easy way to remember it. What do you call this? Don't say tape dispenser. This part right here. Don't say Scotch tape. Scotch tape is the copyright name of it. This right here. Adhesive tape. I am using adhesive tape to bond paper to board. I am bonding 2 different things together. So adhesion is when you are clinging 2 different substances together. So if adhesion is bonding 2 different things together, then what do you think cohesion is? It's when 2 of the same substances are bonded to each other. Adhesion, 2 different things. Cohesion, 2 of the same things. Easy way to remember it. Surface tension. That is the measure of how difficult it is to stretch or break the surface of a liquid. Water has the highest surface tension of all liquid things. This is the basilisk for you Harry Potter fans. Sorry. Chamber of Secrets, not the real basilisk. This is the real basilisk, also known as the Jesus lizard. Because when it has enough distance and it gains enough speed, it can run across water at such speeds that it will not break the surface tension of water and it will not fall through the water, it will run across the water. If the basilisk was to pause, then its weight would be too great and it would actually fall through the surface tension of the water and go to the bottom of the lake. It's able to run across it, so it basically tiptoes on it and it runs across and doesn't do that. If you're interested in seeing a video of this, you can definitely Google it yourself. I also have a pretty cool video. I'll happily put it on the Canvas website. Just, again, shoot me a remind. I'll gladly do that. Okay? You've got other insects that can also walk on water. A lot of cool stuff. That's because surface tension is so strong. If you have ever belly flopped, you have experienced the surface tension of water. That initial slap, that initial break of the surface tension, encounter of water surface tension is what caused your belly to hurt so much. And then of course you broke surface tension, you fell through and went to the water. But the initial surface tension of water, the strength of it is so strong, it's equivalent to hitting concrete. And that's why if somebody cliff dives and there's no breaking of that surface tension, there's no waves, or if you're so high up that you're going to, let's feel the parameters to it. So let's just say you're so high up that you don't break it properly, easiest way to put it, that you're going to go ahead and hurt yourself greatly, if not possibly permanently injure yourself. So, surface tension, extremely strong. Kinetic energy, energy of motion. Okay, heat and temperature are very often interchanged in everyday life. They are 2 completely different things. Heat is a measure of total amount of kinetic energy due to the molecular motion in the body of matter. So, if you look at the ocean, right, the world is made up of 75% of water. Wrong name for our planet, that's okay. So 75% of our planet is made up of water. Our oceans have a greater amount of heat than any one person knows. I'm going to say that again. Our oceans have a greater amount of heat than any one person has. However, our body temperature is much higher than the temperature of any ocean. Because our body temperature is 98.6, and even right here in front of Dina, what? Low 80s, I think is where we're at right now, 82, right about there. Because temperature is a measure of intensity of the heat due to the average kinetic energy of the molecules. So it's the molecules moving off. It's the molecules moving, giving off that heat. Okay, it's the average temperature of those molecules moving. All right? I know it's like, splitting hairs. Don't get over worried about it. But this is a measure of the total amount of kinetic energy This is a measure of intensity of heat due to the average kinetic energy of those molecules. So, if I go into the ocean, I'm going to have a higher temperature than the ocean, but the ocean's going to have a greater amount of heat than I am. This right here is why when scientists announced that the oceans went up by 1 degree, they were so concerned because in order to raise all those molecules by 1 degree, it took a whole heck of a lot of energy to do that because there's so many molecules in there. Does that make sense? Hopefully it does. All right? Again, come see me if it doesn't. All right. Now, because it takes so much energy in order to change water's temperature, luckily water doesn't change temperature overnight. What do I mean by that? Okay, we've all woken up in Jacksonville or in Yulee or in Nassau County and somewhere in Nassau County, and it's been 30 degrees in the morning, and by the time 4 o'clock came around, it was 70 degrees. So it's a 40-degree jump, right, in one day. Did the temperature of the ocean in Virginia Beach change by 40, or Jacksonville Beach, change by 40 degrees? No. Okay, you're lucky if it changed by 1.5 degrees, and that's really only because that was at the beach and the water's really shallow right there. You're not going to change that much. Now, as much as air temperature might have changed 40 degrees, ocean temperature didn't. Arizona, 2 summers ago, they had highs of 120 degrees, so bad that they had mailboxes. So you had the wooden post and you had the plastic mailboxes. The mailboxes melted around the wooden post, and your trash cans were parts of it melting down because it was so hot. So it was 120, 130 degrees. Now, that was during the day. At nighttime, it can drop down into the 30s. So you're talking almost a 100-degree drop in the same day. Again, extreme situation, just like for us, but it can happen. What's the difference between the desert air and our air? Hopefully, you're saying humidity, right? So what is humidity? Water. That's all it is. We have water in our air and they don't. So it's a lot easier to change their air temperature 100 degrees than it is to change ours 100 degrees. As annoying and frustrating as it is when it changes 40, 50 degrees in one day, it's so much worse when it changes to 100 degrees in one day for them. So our temperature, our weather tends to be more consistent, if you will, than theirs. Because we have that humidity, we have that water, because it takes so much more energy. Now, I have a tank in the back of my classroom. My tank can handle, my organisms in my tank, my fish and my corals, they can handle a change in temperature about 4 or 5 degrees. If I were to all of a sudden come in and they like a nice 80-degree temperature, if I came in and janked them up to 90 degrees overnight, they might be able to handle it for 1 day, maybe 2 days, but after that, they'd all be gone. Because they're not used to a 10-degree change. Well, what the heck? We can handle a 40-degree change. Are they wimps? No. They're just not used to that. They have not been adapted to that because water doesn't change 10 degrees overnight. Because it takes so much blooming energy to do that because they have so much molecules, so many molecules. Make sense? All right. This is just English Channel. This was the first guy who swam it. I just thought it was interesting. He covered himself in bear fat to swim it, and it's just the idea that, you know, this guy again might have more of a higher temperature than the English Channel, but he definitely has less heat than the English Channel. By the way, where do you lose most of your heat from in your body when you're swimming? From your head. Why? What do you not have in your head that you have in the rest of your body? Fat. You don't have any insulation, so you actually lose, I believe, 60 to 70% of your heat from your head. That's why when babies are born, we put little hats on their heads, because they're not really good at thermoregulating, keeping that homeostasis. So, interesting fact. Okay. again, this is all white. You only need to know the yellow. It's just interesting. It's just to remind you that calories are a form of energy so that you can get things done. So when you eat, it's so that you can perform cellular energy. You can get cellular energy out of ATP, those 3 letters, those dang on 3 letters. So I just show you a little picture right here. 5 pounds of spaghetti can brew 1 pot of coffee. 1 piece of cheesecake can run a 60-watt old-fashioned incandescent light bulb for an hour and a half. 217 Big Macs can run your car 88 miles. Now, please do not go and shove 217 Big Macs into the gas tank of your car. You will do serious damage. It's just to get you to understand the concept of it. All right? I always like that. By the way, we like to talk about calories in our food. Like, a Snickers bar is 235 calories. It's not. It's 235 kilocalories. We just dropped the kilo part because, yes, number 1, we don't do the metric system. Number 2, we don't want to feel bad about ourselves because even in places where they do the metric system, they don't say kilo because they don't want to make you feel bad. So when they say 235 calories for a Snickers, it's actually 235,000 calories. That tells you how much energy we need to get through the day. Specific heat, amount of heat that must be absorbed or lost of 1 gram of that substance is changed by its temperature by 1 degree. Specific heat of water, 1 cal per gram per degree Celsius. Specific heat of ethyl alcohol, 0.6, almost half of that of water. Thanks to hydrogen bonds, you need a whole heck of a lot of energy to break your bonds. Okay? All of that right there takes a whole lot of energy. Again, that's why we're going to have a more consistent air temperature the closer you are to the ocean than you are in the desert. Okay? Because of that humidity in the air, because the amount of specific heat it takes, the amount of energy it takes to change the temperature of water. All right? Evaporative cooling. Evaporation, also known as vaporization, the transformation from a liquid to a gas, aka sweating. This is what cools us down. Heat of vaporization, quantity of heat a liquid must absorb for 1 gram of it to be converted from a liquid to a gaseous state. When we sweat, it's not the actual sweat that is what cools us off. It's when that sweat leaves our skin and turns into a gas around us. That is what actually cools us off, because that liquid needs to come off of our skin. So when that liquid starts absorbing the hotter molecules around our skin, so it goes from a liquid state to a gaseous state, that's what cools us down. By the way, where do you find the hottest foods? Spiciest foods. You're going to find them in India. You're going to find them in Mexico, South America, Africa, Asia. What do you start noticing about all those countries? Where are they located? Right around the equator. So why would you find spiciest foods around the equator? Well, what do you do when you eat spicy food? You sweat. So sweating cools you down, so you eat spicy food so you sweat so that you can cool down, and you do that where you live where it's really, really hot. So you eat spicy food where it's hot so that it cools you down. Kind of cool, right? So, makes sense. Now, thanks to hydrogen bonds helps moderate the Earth's climate. Evaporative cooling, the highest molecules, those with the most kinetic energy, are most likely to leave as a gas. Dogs can't sweat, not the way we do, not through our skin, so they pant. You have to be very careful with dogs because they need that panting capability because that's how they maintain their homeostasis. That's why you have to be careful with putting muzzles on them. You really don't want to put their muzzles on them for more than 30 minutes at a time, because without that, if you do, then they can't bring their body temperature back down. They can't cool themselves down. So be careful. Not saying go up to somebody who has a muzzle on their dog and yell at them and tell them that they're not doing something right. Please don't do that. Just saying, if you have a dog and you happen to have to put a muzzle on them for whatever reason, just keep in mind no longer than 30 minutes so that they can thermoregulate properly. Homeostasis. Homeostasis is the word of the day. Water is less dense as a solid than as a liquid, making it float. Okay, so what does that have to do with life? All right. Density, formula for density, is mass divided by volume. We agree? So if you take the exact same amount of water, but you freeze it, right? So now these same water molecules push away from each other. The mass stayed the same, but the volume increased, making the density go down. So if it's less dense, the ice is going to float. If the ice floats, look at this picture right here. Here's your ice. It's floating on top of the water. So the liquid water beneath it, it becomes insulated by the solid water, the ice above it. That ice becomes an insulation barrier, protecting the life beneath it from the cold air above it, allowing the life beneath it to continue. If ice sank, then you would have every lake freeze from the bottom of the lake to the top. That meant every single winter, life would start all over again. And if that happened, then your ecosystems in your lakes and your ponds would just be a whole mess every single year. Okay? That would be ecological succession issues, which we'll talk about, and actually BSC 2011. It'd be a whole mess. So, we can't have that happen. Think about it, igloos, right? Igloos are made out of what? They're made out of ice. So homes are made out of ice, something that's cold. Why? Because that ice is causing insulation, trapping the heat inside the little igloo so that the cold air above it stays out and doesn't cool everything inside the house. So that heat is trapped, keeping everything inside nice and warm. That's the same thing that's happening here. By freezing above the water, you're trapping the cold air outside of the water, keeping life beneath it alive. So here we go, we've got a little jellyfish and the diver taking cool pictures of that jellyfish. Okay, 9 more slides. Solid of life, solution. A liquid that is a completely homogeneous mixture of 2 or more substances. Water is a universal solvent. The way you remember it is water, W, is your solvent, VW, solvent, water, solvent, water, solvent, water. In biology, alphabet is your friend. I cannot tell you how many times the alphabet will give you the answer, okay? Solvent, water. Water is universal solvent, dissolving agent of a solution, usually a liquid. Solute, it's what is dissolved. It can be salt, sugar, Kool-Aid guy. Aqueous solution, one in which water is a solvent. Nice and simple, aqueous, think of agua, water. Boom, moving on. When you put a solute into the solvent, these are water molecules. The water molecules, which again are polar, plus and negative ends, are going to come around and surround those ions. The part that's coming up to this particular ion is the ears, the hydrogen end. The hydrogen have a positive charge. So if this right here is sodium chloride, sodium has a positive charge. Chlorine, because remember, he gives away an electron, because he's in group 1, easier to get rid of 1 than go find 7. Chlorine has a negative 1 charge, easier to find 1 than get rid of 7. So, what is this? If the hydrogen ends are bonding to this, is this your positive charge? This is positive right here. Positive hydrogens. Is this positive or is this a negative? Is this sodium or is this chlorine? Opposites attract. That's your chlorine. Okay? Go to this side. Hydrophilic and hydrophobic. If you have a phobia for something, you hate it, right? Hydro, water. So hydrophobic, you hate water. Hydrophilic, you love water. Simple as that. Okay? We're going to talk about hydrophobic and hydrophilic a little more detail when we talk about the cell membrane chapter, which will be coming up. That's really all I need you to know for this slide. molecular mass, you're going to end up the mass of all the atoms in a molecule. So if we're trying to figure out sucrose, sucrose is C12H22O11. So you have 12 carbons. So what you have to know is the mass of carbon on its own. So you have to look at the periodic table. Carbon happens to be 12. So 12, and there's 12 of them. Plus hydrogen, there's 22 of them, and it's 1. Hydrogen weighs 1 gram. Plus oxygen, which weighs 16, and there's 11 of them. When you add them all together, you're going to have the molecular mass of sucrose. That's it. You won't have to do this for me. Just want to make sure you're okay with that. Moles, 6.02 times 10 to the 23rd. Avogadro's number. Molarity is number of moles solute per liter. Again, just a little chemistry flashback. If you're going to be taking chemistry in college, feel free to come back and see me for this, but we're okay for our sake. Okay? I will be testing you on this. pH. Oh, pH. You need to know pH. You need to know pH like the back of your hand. All right? We're going to do some problems with this. Scale of pH. Do you happen to remember what is the range of pH? Can you angle it a little bit this way? It's okay. pH goes from a scale of 0 to 14. All right? Smack dab in the middle is 7. All right? Now, less than 7, you are an acid. Greater than 7, you are a base. How do you remember that? What comes first, A or B? A. What comes first, 1 or 14? 1. That's how I remember. 7, smack dab in the middle, is neutral. Okay? If your pH equals 3, who are you? You're an acid because you're less than 7. Okay? Now, here's where things get interesting. The amount of hydrogen in a solution and the amount of hydroxide, whoa, where did I come from? I'm going to explain that in a second, has to equal 10 to the negative 14. Oh, look at that. 14, 14, 14, 14. We're connected. This came from the splitting of a water molecule. There's a water molecule, and it's split into hydrogen and hydroxide. Now, remember we talked about hydrogen in chapter 2? We said a hydrogen was simply had an atomic mass of 1. An atomic mass is equal to protons plus neutrons, right? And the atomic number of hydrogen is also 1. So that would equal 1 equals 1 plus N. So N would have to equal 0. So protons equal 1, because that's the atomic number. Neutrons equal 0, and then the electrons has to equal 1. Because these two guys have to equal each other, because we don't have a charge on hydrogen. But now here I have a charge. Remember, I have a positive charge on an ion. I'm a cation. So, if I have a positive charge, I have more protons than electrons. That means I have 0 electrons. That means I am just a proton. That means all this is right here is a proton. You really can't have that happening. So this right here isn't true. You can't have a single proton floating around. We're going to add a 2 right here. And we're going to add an entire water molecule to this. H3O plus. And this is called a hydronium ion. Okay? This is a hydroxide ion. OH is hydroxide. Okay? So, back over here. Hydronium ion or hydrogen ion, it means the same thing. Okay? This is the proper way of putting it, but you might see it like this. So I just want to make sure you're familiar with both, no matter what gets thrown at you. Okay? So, if my pH equals 3, my pOH is going to be 14 minus 3, which is 11. Now this is still an acid because it's all based off of your pH. Okay? It's all based off of your pH. Then you would write your hydronium ion, also known as your hydrogen ion concentration, as 10, always, ooh, I said always, you won't hear that often from me, to the negative, always negative, I said always again, 3. Whatever your pH is, that goes smack dab right here. And then your hydroxide ion concentration is 10 to the negative, always, 11. It came from your pOH. All right? I'm about to erase this and do it again. Do another problem. This time I'm going to give you the pH of 12. On your own, I want you to give me the pOH, hydronium, remember, same as the hydrogen ion concentration, and the hydroxide ion concentration. My pH is 12. My pOH is 14 minus 12, which equals a 2. This would be a base because it's greater than 7. The hydronium ion concentration, always 10 to the negative, pH, which is 12. The hydroxide ion concentration is 10 to the negative, always, pOH, 2. Okay? Got any problems with this? I'll be happy to do some more examples at our next night, or come in before the night class, I'm happy to. Acid-base neutral, it's just showing you more. Here's what I want you to notice down here on the pH chart. Hydrochloric acid, pH of 0, very, very bad stuff. Gastric juices, orange juice, wine. So gastric juice, that's your stomach. So your stomach acids, pH of 1.5. So if you're sick and you throw up, that's why it can burn your throat. That's some pretty acidic stuff. Coffee, or us coffee drinkers, pH of 5. Milk, right? If you have heartburn and you drink milk, you're still putting acid in your stomach. It might make you feel better, but it's false because it's still an acid. It's not going to help. Okay, pure water, not the water we get from our tap. True pure water is pH 7. Blood, 7.5. Ask me about holding our Breath. Okay, breath holding. I'll tell you about that. Okay, salt water, just under an 8. Now, detergents, ammonia, bleach, sodium hydroxide, all of our cleaning products, except for vinegar. Vinegar's over here. All of our cleaning products are over here. They're all bases. Okay? All of our cleaning products are bases. I need you to know that. Blood, semi-neutral. Orange juice, wine, coffee, definitely acidic. Then neutral for blood, for water. Then cleaning products, basic. I need you to know that. That's just going over what we did. Okay? Those problems we did onto the side. Buffers. It's a substance that will minimize the change in the solution of hydrogen hydroxide in solution. All right, I got to tell you the blood example. When you hold your breath, if you hold your breath, how long are you going to go before you pass out? About 45 seconds. Okay, most people can hold their breath for about 45 seconds. If they go much more than that, they start getting some trouble. Eventually, they have to start breathing, right? They have to go, they have to breathe. Why? And if you tell me it's to cause brain damage, then let me ask you this next question. Then why is it that if someone has a heart attack, you have 3 minutes to start CPR before they have brain damage? Why is it if we stop breathing, we only have 45 seconds before our brain tells us you breathe, before I make you pass out and involuntarily breathe on your own? But if we have a heart attack, our brain has 3 minutes before brain damage starts. Why the difference? Here's a hint. It's got nothing to do with oxygen. It's the opposite. It's carbon dioxide. The reason your brain makes you pass out when you do breath holding activities, don't do it by the way, is because your body is telling you that your carbon dioxide is actually building up in your blood. When you hold your breath, the carbon dioxide, which is in contact with your blood, and your blood is mainly made of what? Water. And when carbon dioxide is added to water, it becomes carbonic acid. Oh, an acid. So blood, which is about 7.5, you keep adding an acid to it. That blood, which is going where in your body? That's right, everywhere. That blood that's going everywhere is now going to travel with an acid everywhere. Through your heart, your lungs, your brain, your kidneys, your liver. That acid would be going everywhere. Your body can't do that. So after 45 seconds, your body goes, breathe, or I'm going to make you pass out, hit the deck, and you're going to breathe on your own. And that's what it does. If we don't breathe, it makes us pass out, and it makes us breathe. Not to breathe in, but to actually to exhale. Because when we exhale, we release the carbon dioxide, which was mixed into our blood or water, and the carbonic acid is now dropping in level, so we no longer have an acid in our blood. Okay, so how come we're able to make it 45 seconds? Because of buffers. We have buffers in our blood that can allow our blood to go from that 7.5